Our chapter introduced index notation and have shown how elements of tensor algebra is applied to derive new quantities. And you can always apply tensor transformation formulas to find components of tensors in different coordinate systems. And these concepts are going to be used in chapter 2, which deals with definitions and properties related to deformation of a body. And those are mainly strain and displacement. And we will see how tensors are introduced, how they represent deformations of a solid body, and how these quantities can be computed in different coordinate systems in different directions. It's called transformation. It's necessary to find maximum stresses or principal stresses or directions in a deformed solid structure. So these concepts are introduced here in chapter 2, and that is analysis of strain. Strain is related to deformations of a body. And when you consider a loaded body, deformable body as shown in this figure, you should think about its deformations as well. Let's call it the deformed shape. Now this is a B, and the solid line or the green line is the undeformed configuration of this B, original state, where there are no forces, stresses. But then you load this or apply forces to this, it will undergo deformations, and the shape of the body is going to be changed. And the dashed line shows the deformed shape of this B, or deformable object. And this is because of displacements of points in space. We have an exaggerated picture here of both deformations and displacements, because we'll be talking about small deformations of solid bodies. But in an exaggerated view, point A located here is the original location, will undergo displacement and it will move to A prime, or another point B to B prime. But is there a schematic way of quantifying displacements of the body? Because the larger the body, the larger the displacement. And we need a certain way of normalization. And therefore, displacement is a separate quantity. In addition to this, we can define a number of strain components. As a deformable object, in a rigid body, there are no such deformations, and distance between 2 points remains unchanged. This is the original vector covering the distance between A and B. So examine behavior of such a vector. In a rigid body, these dimensions or the orientation of this vector is not changed. But we can first define displacement for a deformable object, again on an exaggerated view like this because we are actually dealing with infinitesimal deformations. This belongs to the category of large deformations, but we will consider infinitesimal deformations, but in such sketches, you can show the deflections as large quantities. In a coordinate system like this, point P moves to another point P prime, and the vector connecting these 2 points is named as displacement vector. It's displacement vector U. It's the undeformed configuration. Under the effect of forces, this will enlarge or contract. And in our notation, the quantities will be written in terms of the original coordinates. For example, this displacement vector of a point P will be written in terms of coordinates of P, or displacement vector U is a function of x1, x2, x3. Those are the coordinates of this point, not the other point. It's this point P. And U is then U1, E1 heads, U2, E2 head, plus U3, E3 heads in this coordinate system. U1, U2, U3, these are scalar components of displacement. Each scalar component is a function of the coordinates x1, x2, x3. And a component is the difference between the coordinates, for example, ui, that in index notation, we are introducing index notation here, ui is then xi prime minus xi, final position minus the initial position. These are the elements of u. It's called displacement vector for points P, and it's in the general formulation. It is going to be found as a function of these coordinates. Is the general definition. This requires the development of a number of equations, but first of all, how can we quantify deformations in a dimensionless sense? To be able to do this, you need to examine small deformations of a body. We consider 2 points, original points, located on a deformable body, P0 and P. Coordinates of P0 are x1, 0, x2, 0, and x3, 0. Coordinates of the second point are x1, x2, x3. Now the coordinates of the second point. Then an infinitesimal vector connects these 2 points. We assume that the size of this vector is infinitesimal, it's A. Now the orientation and length of A is going to be changed. There is going to be a rigid body rotation and stretch or an extension on this vector. At this point, PO moves to PO prime with these coordinates x1 O prime, x2 O prime, x3 O prime. This point P moves to P prime with coordinates x1 prime, x2 prime, x3 prime. This is A. This UO is rigid body translation of this point from this location to PO prime. This is the rigid body translation of point P to P prime. And I can identify deformation measures in an indirect way. Form a parallelogram here One side of this parallelogram is UO, and the other side is vector A. In other words, we are placing vector A here. And now triangles are formed here. For example, in this triangle, A plus this vector is A prime. This is the final vector, A prime. And this increment, vectorial increment, is delta A. This is called deformation vector. This deformation vector is representative of deformations at this location, PO. And in the other triangle, U sub 0 plus delta A is U. And delta A is named as deformation vector. We can now, or we will, introduce a Taylor series representation to be able to find components of this deformation vector, delta A. How can I find components of this vector? We will expand displacement into a Taylor series around PO. There are two neighboring points here, PO and P, and we are going to expand this general displacement U into a Taylor series around PO. Well, what's that Taylor series? UI is this displacement, U, displacement of a generic point P, and expand UI into a Taylor series around PO as a three-dimensional Taylor series. There are variations in x1, x2, x3 directions. I'll review Taylor series representations. You can refer to your calculus book on this. But three-dimensional Taylor series expansion can be written in this form, in this here notation. UI, there's displacement, is UI0, displacement of this point, because we are expanding the series around this point, plus the UI dxj, derivative of U times the increment xj minus xjo. And then there's a sum here noted from 1 to 3. There are three terms here, because there are increments in x1, x2, x3 directions. And now the second derivative of U times xj minus xjo times xk minus xk. And you can add as many terms as you want. But we will not be dealing with a full Taylor series expansion, because this is an infinitesimal vector. We are examining deformations of two neighboring points. This length is small. In such a case, this products xj minus xjo. These are infinitesimal quantities, and their products can be ignored. And we will end up with a linear representation of UI around point PO. Keep or retain only the first two terms. There's the simplified Taylor series expansion of displacement around PO. UI is UIO plus another vector, and this is the other vector. But if you consider this triangle, UI actually is UIO plus this vector, delta AI, which means that the second term, this has to be equal to what? What is the sum equal to? It's delta AI, because UI is UIO plus delta AI. Now we have an expression for delta AI in terms of derivatives, or named as gradients here, times differences in coordinates. Delta AI is delta UI dxj computed at O times xj minus xjo. I goes from 1 to 3. And this term xj minus xjo is, these are the components of A, x1 minus x1, or x2 minus x2, and x3 minus x3. These are AI. So delta AI is ui dxj or times aj. Now this derivative computed at O as gradient, and we have talked about gradients in the previous lecture. Gradient of a scalar and gradient of a vector. And this is gradient of a scalar, and this, we know that this is a second order tensor. We are going to designate this as alpha ij and call it displacement gradient tensor. These elements of the deformation vector depends on alpha ij, displacement gradient tensor. This is a 3 by 3 matrix, and I've written the explicit form of this 3 by 3 matrix here. Alpha 1, 1 is du1 dx1. It means u1 comma 1. Then you have u1 comma 2, u1 3. All derivatives involved here. Alpha ij is therefore this matrix computed at point O, PO. Now we can examine this tensor further to define additional tensors here. Now, alpha ij, displacement gradient tensor, is defined, and any tensor can be written in such a form. This is a simple expression of identity, because now if you add them up, see that right side is equal to alpha ij over 2 plus alpha ji over 2 plus alpha ij over 2 minus alpha ji over 2. These are cancelled out, and this gives alpha ij equals alpha ij. So to this tensor we have added and subtracted alpha ji. Why do we do this? Because this results in the computation of some physically meaningful quantities. In such a deviation, or for a general tensor like this, the first term, 1 over 2 alpha ij plus alpha ji, is always a symmetric tensor. We will denote this as epsilon ij, and the second one, 1 over 2 alpha ij minus alpha ji, is always a skew symmetric tensor, and we are going to denote this as omega ij. In a symmetric tensor, epsilon ij equals epsilon ji. And you can easily show this, I think. Alpha 1, 2, for example, equals, or for epsilon 1, 2 equals 1 over 2 alpha 1, 2 plus alpha 2, 1. Epsilon 2, 1 is 1 over 2 alpha 2, 1 plus alpha 1, 2. Alpha 1, 2 is equal to alpha 2, 1. Epsilon 1, 2 is equal to epsilon 2, 1. Here, I show that omega 1, 2 is minus omega 2, 1. Omega 1, 1 is 0. 1, 1, 2, 2, and 3, 3, they are all 0. This skew symmetric tensor. Now, starting with this general tensor alpha ij, we ended up with two separate tensors, epsilon ij and omega ij. The first one is symmetric. The first one is called strain tensor. It's representative of deformations of a body, as we will show later. And the second one is called rotation tensor, and that is representative of rigid body rotations of vectors, infinitesimal vectors located on the body. And the first one gives stretch or contraction of infinitesimal vectors. The second one representative of rigid body rotations. In summary, epsilon ij is called strain tensor. We will look into the properties of this. And omega ij is called rotation tensor. So how are these calculated, or why do we define this in the first place? We have defined these because alpha ij is written in a different way, and it's equal to epsilon ij plus omega ij. And where did this come from? Delta ai is alpha ij times aj. And this is delta ai, it's alpha ij times aj. And alpha ij is just written as epsilon ij plus omega ij. Substitute here. Substitute alpha ij here. Then you will get delta ai as epsilon ij aj plus omega ij aj. And substitute delta ai in this result. You get ui equals ui0 plus epsilon ij aj plus omega ij aj. One final result for the displacement of u. And what do these terms stand for? Displacement of a point. It's written by means of Taylor series expansion. It's written in terms of quantities calculated at all. UIO, this is called rigid body translation for this point. Omega ij aj, that accounts for rigid body rotation, plus epsilon ij aj, and this accounts for actual deformation. How can I show this on a diagram? Suppose that this UIO is 0. The tail of the vector is fixed. If this is AI, there is an A prime vector here. Translation term is 0. And AI plus delta AI is AI prime. B1 is AI prime. And delta AI can be decomposed into two components, which are written here in this equation already. One of them is epsilon ij aj. Delta ai is a sum of this vector, epsilon ij aj plus this vector, omega ij aj. Now, omega ij aj is representative of deformations of this infinitesimal element, rotations of infinitesimal element, because we can show that this omega ij aj is perpendicular to A. This vector is perpendicular to A. It does not therefore contribute to stretch or contraction of A. This term is responsible for from stretch or compression epsilon ij aj. Now we can find basic results showing that this vector omega ij aj is perpendicular to AI, or the angle between them is 90 degrees. And you can show it by simple vector algebra. Evaluate dot product of this vector AI with this vector omega ij aj. If they are perpendicular, that dot product should be equal to what? dot product of AI and omega ij should be equal to 1 if they are perpendicular. 0, yes, and Antoinette gave the correct answers. Now, if dot product is 0, that also means that they are perpendicular or orthogonal. And how can I find dot product of, or how can I write dot product operation in this here notation? We have a vector AI, and this is a vector omega ij aj. Dot product of two vectors, AI and BI. How can you write it if there are two vectors, AI and BI? How can you write their dot product? Or AI and BJ? The dot product is A1B1 plus A2B2 plus A3B3. So AIBI is a simple representation for dot product, and dot product of these two vectors is AI omega ij aj, or omega ij AI aj is dot product of these two vectors. And I can evaluate this or simplify this, expand this, because there's a summation over I and J. I and J are both dummy indices here. And if you expand this, you'll get, for example, omega 1, A1 square, omega 1, 2, A1, A2, plus omega 1, 3, A1, A3, first row. And increase I by 1, you'll get omega 2, 1, A2, A1, omega 2, 2, A2 square. Goes on like this, up to omega 3, 3, 3 square. Omega rotation tensor is skew symmetric, and its diagonal elements are 0. Hence 1, 1, 2, 2, 3, 3 are 0. And the other terms cancel each other. Omega 1, 2 is minus omega 2, 1. Omega 1, 3 is minus omega 3, 1 in a skew symmetric tensor. Omega 2, 3 is minus omega 3, 2. These are all cancelled out. Everything is cancelled out, and this is 0, which means that the angle between these two is 90 degrees. They are orthogonal. So this vector is not representative of deformations. It's representative of rigid body rotation of this. And that's because of the fact that these are perpendicular to each other. This vector epsilon ij is related to stretch or contraction. This. Now, two vectors are defined, two tensors, epsilon ij, strain tensor, and omega ij, rotation tensor. The first one is a symmetric tensor by definition. Second one is skew symmetric. And an expression for displacement is also found in terms of these tensors. And now we will examine these tensors in more detail, and we will see how they represent displacements or deformations and rigid body rotations of a deformable object. Any questions about this point? Let's have a break then. We will continue our discussion after the break.